So, thank you very much for having me here. And yes, it's not only about why programming languages matter, it's about why they matter for security, because we had a security conference here, obviously. So, what qualifies me to talk about programming languages in the context of security? You know, I'm a hacker. I started cracking games when I was 14 in the 80s, and then I got bored and started writing software, and then I needed money, so I started working as a pen tester and did pen testing, did security consulting. Then I got bored again by a lot of, seeing the same problems over and over and over again. You know, you come to customer and they say, look at our website, and you find a couple of SQL injections, you find a couple of cross-site scripting exploits, and it's the same repeating over and over again. So I'm pretty happy to have developed to a position where I'm now a security architect, which means I help building secure software. I help the people who write software to build them in a secure way. And that's also, of course, the other part of my career. I've been a long-time member of the Chaos Computer Club. I've organized the CCC Congress for a couple of years together with others. And I worked on a compiler, a programming language called Dylan that many people don't know. But we ended up winning top places in the ICFP programming competition with that compiler. So I know about writing software, I know about security, I know about compilers, I know about programming languages. And I try to put that into practice in my role as a security architect in our company, which makes maps, by the way. Many people don't know us, but if you own a car and it has a navigation system, there's a more than 90% chance it's our data and our software that drives that. Okay, so for those of you who have been listening to a lot of talks today, let me give you like the 2-minute summary of my talk. And this is why choice of programming language matters for security. Is wireless mic? Let me try that. Test 1, 2. Excellent, thanks. Much better. So the thing is, programming languages. If you come from university, they probably told you about Turing machines and Turing completeness, and that in a technical sense, all programming languages are equivalent, which is true from a mathematical point of view, but at the same time not true from a user's point of view. You have to ask yourself, why do programming languages exist at all? Computers are happy with zeros and ones. You could write a program by flipping zeros and ones, machine code instructions, not even assemble it, just raw hex values, put that in the computer and the computer would happily run it. So the truth is, the only reason programming languages exist is for the human user writing it, and even more for the human user reading it. So there's a purpose in programming languages, and they're not all the same for the convenience of a user. If you've ever tried to write a complex piece of software in C compared to, say, Perl or Ruby or Haskell, you know that it's not the same amount of work that goes into writing a piece of software in a certain language compared to another language. Because programming languages also have different abstractional capabilities, and programming is all about abstraction. It's all about making the amount of information that you need to keep in your head while designing the program manageable. You need to break it down in something that fits into your brain, because the brain isn't so big compared to like the huge state space of your program in the end. You can only look at so many lines at the same time, think about so many problems at the same time. So you need to break it down. Writing software is the art of abstraction, is the art of engineering, of breaking the problem down into manageable sub-problems until at the end you arrive with a total program that works. But let me get into the details. So what are programming language features that are a security problem? Typical security problems. Let's start with the one that's obvious, spatial memory safety. How many people here have written software in C? Show of hands, who's writing C? Okay. Do you think you can write secure C software? One, I challenge you. Challenge is coming up later. You know, first, for like the very easy case, that's like your standard 70s vulnerability in a piece of C software. So what's going on for the people who do not know any C is like you're getting in a character pointer, so pointed to some byte data. And you copy that to a buffer with a string copy function. The string copy function strings in C are terminated by 0, so it copies in bytes until it sees a 0. And on the stack here is a variable called buff allocated. And if there's more than 16 characters in the string in the input, it happily writes all over the rest of the stack. And on the rest of the stack is the return address. And if my string as an attacker is longer than 16 bytes, I can influence the return address of the function, thus make the program jump to somewhere else under my control, which of course then leads to exploits, etc., yada yada. Old problem, like the 1988 Morris worm used an overflow like that. There are some variants of that. You can have heap overflows, like if the memory isn't allocated in a stack, but manually allocated on the heap, you essentially have the same problem. You copy in there. And of course, so now probably most of the people writing C would see the problem with that, right? So who's seeing the security vulnerability in this piece of code? Like we have a buffer of 1024 bytes. We're getting in some structure foo and a count, a number of foos we're getting in. And then we multiply the size of the structure by the number of structures we're getting in. And we look whether it's less than 1024. And if it is less than 1024, we copy it into the buffer. And if it isn't, we don't. Okay, who's seeing the issue here? Nobody? Oh well, nobody of you should ever write any C code. Please don't, just don't. But let me explain what's happening here. Integers in C are not like integers in mathematics. If you keep adding 1, 1, 1, 1, 1, eventually the integer will overflow, become negative. You see where that's going, right? If count is high enough, so that when I multiply the size of my structure by the count is more than the range of my integer value on the platform, it becomes negative. And all of a sudden, I put in like 100,000, a million items, and the multiplication turns out to be negative, so it's less than 1024. And the program happily starts copying stuff, copying it all over my RAM, and again, boom, software is exploitable. Of course, if nobody saw that, I think nobody's getting that either. This is a very tricky thing. So I just explained, right? If you multiply stuff, it can overflow and then can be less than 1024, even though the data structure coming in is much, much larger. So you could be clever and say, haha, I'm going to check for overflow. I'll check if the result is negative. That's what's going on here. Like, I check if the result of that multiplication is above 0. Because if it's above 0, some evil hacker is trying to mess with me, right? Thing is, that doesn't work either. Why doesn't it work? Because the overflow of signed integers in C, according to the language standard, is undefined. And what's going on is that the compiler sees this and says, you know, there's a multiplication, the result of that multiplication is undefined. If it's undefined, I as a compiler can do whatever I want. So what do? Well, how about not doing it at all and ignoring the result of that computation? So even though we think we put in a check for the overflow case in there, actually we didn't, because the compiler optimizes it out. Which is bad, like really, 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 really bad. And nobody's seeing that. A lot of people are writing C. The better ones realize that they're not very good at writing secure C and taking extra care, but bugs like that almost nobody is seeing. So, what do we do about that? You know, stop writing C. Like seriously, if you write software today, there are some corner cases where maybe writing C is okay, and that is if the alternative would be writing assembler. Say you're writing a software for a small microcontroller that only has 4 kilobytes of RAM, okay, go ahead, use C. Write something connected to the internet? Hell no, don't do that at all. Like even Pascal, Turbo Pascal, like in the 80s, had bounce checks. You could say, whenever I access an array, please tell me if I overflow my memory. Like in the last 2 years, we had almost 3,000 CVEs that were buffer overflows of the kind I just shown you. Like we could completely eliminate it by not using C as a language or by using any language actually that does proper bounce checks on arrays. There's more problems with memory in C. That's temporal memory safety. So we're talking, last thing we talked about was spatial memory safety. That means we accessed a space of memory where we didn't belong to, where control information for the control flow of the program is, which allows an attacker to write attack code. Now we're talking about temporal memory safety. What's temporal memory safety? That is, we're accessing a piece of memory that once was proper piece of memory and valid, but isn't any longer. How does that happen? One very common case is we allocate a piece of memory with malloc, we free it again, and then we access the memory. Like in that case, it's blindingly obvious, right? If you look at that piece of code, you see it's broken. Usually the point of allocation and the point of freeing stuff is not so close together, so it's hard to see. And that's the thing, that's the point I'm trying to make. The language is making it hard to write correct software by forcing me to care about that stuff like that by hand. But that's not the only situation where something can go wrong in C. That's also a favorite, like free the same thing twice. So I allocate memory, do something with it, free it, then do something else that also allocates memory, which allows the attacker to write to the internal data structures that maintain the memory. So if you allocate a piece of memory using malloc in C, it allocates pointers that point towards the next free block, etc., etc. So it uses management information that you can overwrite in a heap overflow. And when I do free again, it tries to link the block of memory to a free list. And for doing that, it accesses certain pointers that I might be able to control in the something harmless function as an attacker. So the second time I free the memory, I have already freed. It's interpreting data that an attacker supplied and interprets it and allows me again to arbitrarily write to any memory. That's also a favorite one. Like you have a piece of memory allocated on the stack, and then you return the address of that thing on the stack. And you don't immediately notice, because if you just test it, it might work. It usually doesn't when you do more work in between. So you have a piece of memory that might still contain the bytes you want to have there. But sometimes it doesn't. And an attacker might be able to construct a situation where he accesses that piece of memory. So what can we do about it from a programming language point of view? So since this is 2016, you've all heard about garbage collected languages, like even Java has it, yeah? Right? And PHP and Perl and Ruby and everything else, JavaScript. So use a language with garbage collection, because the compiler and the runtime of your language will take care about your allocation. It will allocate memory for you before you write to it, and will make sure the memory is valid as long as you still have a valid handle to that piece of memory. Just by using a garbage collected language, you have just completely eliminated all those kinds of bugs. You know, go to CVE, look for double free as an error source, and you will find again hundreds and hundreds of errors like that are actual vulnerabilities used out there. There's another interesting design that I would like to point out. That's a language called Rust, which is a pretty recent language done by Mozilla. They're going a different way. What they do is that instead of having garbage collection, they maintain the principle of ownership. And so if you have two pointers, to a piece of memory, only one pointer actually owns the memory. And the other one, you need to actually say, you know, this pointer to the memory I have, that's a borrowed pointer and I do not actually own it. So they have a concept of ownership, they have a concept of borrowing a pointer, and together that means that the compiler at compile time can verify that somebody is responsible for that piece of memory, and that person responsible needs to free it in the end. And it will detect if you do not free it in the correct order. It will detect if you try to access it after freeing it, all by the virtue of maintaining a piece of ownership. So that's a code example here. The red isn't too readable. It's essentially giving an error message that says you're accessing a moved value. You're accessing the memory through a pointer that is not the owner of the pointer, and you should have borrowed it instead of copying it. So very nice and fresh approach. Okay. Injection attacks, cross-site scripting, SQL injection, you probably know about that stuff. I have a very simple example here. You see that all over code. You have an SQL query where a part of the query, that ID parameter here, comes from the outside. And it's just concatenated to the SQL string. And by doing something like single quote, semicolon, you probably can add another SQL statement after that, and as an attacker, inject an SQL command in there. Cross-site scripting looks the same. I didn't bother to put up an example. You probably all know about that. So what can you do on a language level to prevent that? There are two solutions. One is something that Perl had since the 90s. That's so-called taint tracking. That means that any input to your program is marked as being tainted. And if you try to do something like that, the SQL interpreter will say, no, you're using a tainted value here. You have to explicitly, as a programmer, say, now it is untainted. And this gives you the chance to think about what to do against the injection attack, which means properly escaping the input string you're getting, properly doing input validation and whatever you need to do. So that's an approach. I think Ruby has it as well. And the other approach is properly using static types. I will not go into detail. You can look that up. The idea here is that you build a type system where just concatenating strings and putting them into the SQL interpreter would give you a type error. Where in fact, for every place where you can substitute a piece of string, imagine you have a template, and in the template there are substitution variables, that for every substitution place, the compiler knows the grammar fragment that you're referring to, and maps that to a type in your type system. And unless you produce the right type of grammar, it will not type check, it just will not compile. So there's an intermediate step in between that is using a context-aware template substitution engine which does automatic substitution for you. It's also something you can do that's not on the programming language level, that's on the library level, but also a good idea. Oh, this one is one of my favorite. Automatic type conversion. You know, a lot of languages, so-called scripting languages, allow you to have convenience features, like you can add a 1 to a string that contains a 1, and it will just convert the string to a number and give you 2. The thing is, this looks convenient on the first glance, but it will lead you to interesting phenomena. There's that great 2012 video called What? By Gary Bernhardt. Maybe some of you have seen it. I reproduced some of the examples there, and it should give you an immediate idea of how unpredictable that type conversion can be. So if you add 2 square brackets, that's an empty array. If you add a square bracket to a curly bracket, that's an object. Adding a curly bracket to a square bracket gives you the number 0, and adding 2 curly brackets gives you not a number. What? So it doesn't make sense, it's unpredictable. As an author of the code, you have no idea what's going on, you test it and it looks good, works for you. As an auditor, you have really no idea what's going on. And goes on like that. Like, This one. So array of size 16. Yeah, you can join it with the what, and then here you're adding a number one to a string what. What it gives you is it converts the one to a string one, and then concatenates that, so you get a what one. If you do a -1, it gives you a not a number. So this should illustrate you like completely unpredictable things are if you have automatic type conversion in your language. Is that a real world problem? Yes. So this is PHP code. Imagine you're writing a website and has password checking, and it takes the MD5 because you're doing good programming, right? You're here hashing the passwords, you compare the hash that the user entered to what's in the database. And then you suddenly find out that for some reason, PHP thinks the MD5 checksums of these two different passwords are the same. Why? Anybody has an idea? No, it's not MD5. It's not an MD5 attack. I could have used SHA-256 and it would work. Yeah, you have to have 3 equals. And you know why? Because if you look at the actual checksums, they both start with 0e. So PHP in its infinite wisdom thinks that's a string that contains a floating point number. So for comparison reasons, why not convert it to a floating point number, which is 0? And the other one is also 0, so they're equal. And that's actually a real world attack. PHP websites have been hacked that way. So automatic type conversion is bad. PHP shouldn't even have the 2 equal signs, in my opinion. It's like automatic type propagation is evil. You do not want to have it in your language. Choose a language that doesn't have it. What else do we have? Eval. That's a fun one. You probably all know about JSON, JavaScript object notation. Why is JSON so popular? Because it's so easy to implement. You get input from the user, you call eval, and you have a data structure. You call eval on user input. Like exploitation doesn't get any simpler than, just asking the user for what does he want to execute. So more modern implementations of JSON, of course, have a proper parser, etc., etc. But that's a bug that comes up in pretty much all the languages that implement eval. And I've brought you something that's a very old language and a very old program. Might have heard about Common Lisp, from the olden days when people had parentheses. Common Lisp, if you've ever dealt with Lisp, it has a very tight coupling between programs, data, and there's everything in list structures, nested lists. So there are 2 functions. One is print. That's the one on the top line. You can give print a structure so that after the quote sign is, take it literal, and has a list that starts with a foo, and then another list that starts with a bar and has a bus. So a pair of nested lists. If you say print, it turns that into a string. And in the second line, you see the string. And then the opposite of print is read. You give read a printed representation of a Lisp object, which is like the foo bar bus, like the list again with a nested list, and it turns it back into a list. Very convenient. If you write a network service and you need to transmit arbitrary Lisp objects from one server to the other server, you say print on one side, you say read on the other side, and you're done. Easy enough. Until that's something that, in the very early times, one of the first network intrusion detection systems was based on a Lisp machine. It was NCSA developed. You might remember the FSec of the NCSA Dogmaster supercomputer. And as a response to that, they had a program where they developed the first network IDS. And they had then a red team against blue team challenge. And the red team managed to break into the blue team's network IDS system. How did they do that? They used an obscure feature called a reader macro. It turns out that read supports syntax extensions. One of the built-in extensions is eval. And you can just say, you know, hash mark dot, and then an arbitrary Lisp expression. And again, that's evaluated and executed. So you say run shell command calc.exe, and boom, your calc is popped. So make sure you have no eval in production code. It has some uses in some areas, but you should have a language where either eval is not available, or you can conclusively prove that eval is never called into user input, for instance, by having a sane level of module management. Which brings me to my last point, and that's referential transparency. What is referential transparency? That is, if you look at an expression like that, a times a, or foo.bar with an argument bus, can you figure out by looking at that piece of code what it's doing? And the answer is, it depends on the programming language. It depends on what modules are loaded. So, for instance, Ruby is one of those cases. You load some obscure Ruby module, and it goes all the way through the existing Ruby infrastructure into your existing code, and then adds some extra code to it. And you cannot possibly tell what a piece of Ruby code is doing without knowing all the other modules that are eventually going to load it. Because there's no such thing as referential transparency, because every module can override every other module's symbol table easily. And they call that a feature. So what you want is you want to be able to look at a piece of code and figure out, a times a is a multiplication. A must be a number, B must be a number. There must be an interface for numbers. And for every A that adheres to the number protocol, this gives me the square thing, and not something else entirely. You must be able to make sure that loading another library doesn't influence the code that was already there. And this is why you want a language that is statically typed, so you can tell that A is a number in that case, and also a language that doesn't have any side effects. So it's not that the next time you call A times A, you get a different result, because A times A is always the same. So my conclusion here is you want to think about the programming language you use for the task, if you can. So I readily admit there is a ton of reasons that go into choice of programming language for a project, which involves what system are you deploying on, what developers do you have, how well are they trained, what's your time to market, how stable is this stuff, etc., etc. But security plays a role in your choice of programming language. And I think what you do want to have is you want to have static types, you want to have automated bounce checks, you want to have garbage collection, and you want to have a functional language without side effects, because that's the only chance you have to actually, when looking at code, figure out what's going on. Okay. That's it. Thank you for listening. I'm opening for questions. The thing is that the Haskell people, they try to scare you with their math language for describing things. So they're going to tell you, I/O in Haskell is very easy because you need to have an I/O monad. And you say, like, what's a monad? And you say, it's very easy. That's a monoid in the category of endofunctors. What's the problem? But that's the wrong approach. If you teach Haskell to people, you just say, if you want to have a function that produces I/O, it needs to have an I/O type as a return type. That's it. Do not think about the details. And that works. That actually works because you do print. You have a function that produces side effects, that produces I/O, needs to have an I/O type. So it works. Well, I wouldn't recommend writing assembler at all because it allows you to make all the mistakes. Yes. So I mentioned Rust as a positive example. If you're doing like really low-level, systems-level programming for efficient code and you don't trust garbage collectors and you want to be like, you want to have that bare metal experience, give Rust a chance. I really like that. For more high-level stuff, OCaml, but avoid anything that has side effects. So OCaml is not a purely functional language. It gives you like the ref type where you have ref and ref setter. It gives you objects. Ignore that stuff. You take the functional subset of OCaml. That's a very good language. Haskell is a nice language to look out. And then we're already running out of options. If you want to have, you know, at least a certain solidity. So there are people running out there who run like OCaml projects. Jane Street is there in the market of automated trading. So they have a machine that has a very short cable to the New York Stock Exchange, and they're doing automated trading, and they're using OCaml software for that. They're moving billions a day with a piece of OCaml software. There are comparable Haskell projects out there. So these are like, they're used in real world production systems, so you have at least some guarantee. Rust is relatively new, but Mozilla is just writing their rendering engine for Firefox in Rust, and I think that's a good idea to get rid of many of the problems we see in browsers. But yeah, the list is short. But in the end, I said it's a compromise. So I think I mentioned the most important classes of bugs here. If you have a choice between A and B, maybe none of them is perfect, but one is better than the other. You know, if a guy comes and says, you know, we need to write a new piece of web server code and we can do it in C or Python, definitely use Python. It's not a question. It won't perform, but that doesn't matter today because you just fire up 100 Amazon instances and it's still cheaper than the programmer writing the C software. So it's sometimes a trade-off, it's sometimes a balance, but those are my recommendations.